For this one, we have a figure here. This is the wire for segment 1, segment 2, and the third one is a circular arc. So the wire carries a current I and consists of a circular arc of radius r, and the center angle of this arc is pi over 2, which is 90 degrees, and the two straight sections whose extension intersect at the center. What magnetic field B does the current produce at Z? So of course, this one will generate a magnetic field, so as this one and this one. And of course, this is not difficult at all. So using the Biot-Savart law, we can write Biot-Savart law can be written like this. And of course, theta is what we concern. Actually, the theta is the angle between the wire ds. ds for segment 1 is, of course, in this direction. And r is actually like this. This is r. And in this case, theta should be 0. So the whole term will be 0. And also for segment 2, ds is something like this. This is ds for segment 2. And r should be in this direction. So theta is 180 for this case. And likewise, sine theta is 0. So dB is also 0 for segment 2. So we can write that B1 equals 0 and B2 equals 0. For the segment 3, B3 is nothing but mu0 I phi over 4 pi r. This is the formula we get in the previous page, and we substitute phi to be pi over 2, 4 pi r. So we put the 2 at the bottom, so it is nothing but this. Sorry, the pi should be cancelled. Pi should be cancelled. So wait. So this pi should not exist here because we can. This pi and this pi can be cancelled. So finally, we can write the total magnetic field generated by the whole wire is B1 plus B2 plus B3. So which is nothing but mu0 I over 8R. So this is pretty easy. And of course, you also need to determine the direction of the magnetic field, and according to the right-hand rule, the magnetic field at point C should be into the page. You can simply use the right-hand rule. The thumb of the direction of the thumb should match the direction of the current, and actually like this. The flux of the direction of the flux matches the current, and then you use the right hand. So at this point, the magnetic field should be into the page. So any questions? Very easy. Okay, so next one. For this one, two long parallel wire. This is the Y1 and Y2, I1 and I2, carrying current I1 and I2 in opposite direction. I1 is out of the page, I2 is into the page. What are the magnitude and the direction of the net magnetic field at point P? Point P is something like here. Assuming the following value, I1 equals 15A, I2 equals 32A, and D equals 5.3 cm. D equals 5.3 cm, and this is a right angle triangle. This is a right angle triangle. So I1 is out of the page, So we can use right hand rule to see the magnetic field at point P would be pointing this direction. And for I2, using right hand rule, something like this. At point P should pointing to that direction. So we know the direction for B1 and B2. And actually, this is a right angle triangle. So B1 and B2 are perpendicular to each other. And next, we need to calculate the magnitude of B1 and B2. So for B1 is very simple. We only need to use the formula like this. Mu 0 I over 2 pi r. I1, this one should be I1. And R is R. For B2, it is similar. This is only mu 0 I2 2 pi r. Okay, very easy. And actually, R should be equal to D over square root of 2, which is something like 3.5 over square root of 2 equals 3.75 cm. So we want to calculate the magnitude of B, which is this B1 at B2, and they are perpendicular to each other. So we use the Pythagorean theorem. So we have B1 square plus B2 square, and take the square root of them. So it will be nothing but mu 0 I over 2 pi r square root of I1 square plus I2 square. So we substitute all the values. Mu 0 is 4 pi times 10 to minus 7. 2 pi times 0.0375. I is sorry, there's no I there. No I here. No I here. And the rest of stuff is 15 square plus 32 square. answer is 180 mu t. So this is the magnitude of B, and also we would like to know the direction of this vector, and we can see that phi so phi would be arctangent of B1 over B2, which is 15. Over 32. So this is 25.1 degree. And actually this is theta. So theta will be 25.1 degree plus 45 degree. So which will be 70.1 degree. So actually, you know B1 and B2 are perpendicular to each other, so you can rotate your axis so that you only find the square, the sum of square and the square roots, and you calculate the phi of that in that coordinate, and you add 45 degrees. You don't really need to separate B1 into x-axis, y-axis, and then separate B2 into x-axis, y-axis, and add them together, and then you will take more steps and more possible to make mistakes. Any questions? Okay, let's move on. So here, these slides talk about the force between two parallel currents. So first, it tells you that parallel wire carrying current in the same direction attract each other, and oppositely, parallel wires carrying current in opposite direction repel each other. So what does it really mean? So in this graph, you see that this wire and this wire are parallel to each other, and the current of this wire are in the same direction. As they are parallel, you can say they are in the same direction, although current is not really a vector. But as long as they are parallel, you can say, they are in the same direction. They don't need to be the same current. Only the direction of the current concerns. So it tells you that if IA and IB are in the same direction, then these two wires will attract each other. For the second statement, it says that if IB go in the another direction, if this is two wire and this is IA and this is IB, then these two wires will repel each other. FBA, FAB, the magnitude should be the same and direction are opposite to each other. And of course, this one, they are attracting each other. So the magnitude of the force of a length L of either wire is something like this. Why it will be like this is so consider a wire A here. So it will generate a magnetic field here, pointing downward. So this BA is generated by IA. And according to something like the Lorentz force, you'll see that if a current going in this direction and the magnetic field is pointing downward at all points of this wire, so L is in this direction, BA is pointing downward, so you use the right hand rule, the cross product, FEA should point to that direction. And for the other case, similarly, for IA, it generates the magnetic field BA also pointing downward. However, for this case, IB is pointing in this direction, and you use a right-hand rule, the cross product. So FBA should be pointing in this direction. So, so in the previous chapter, we know that FBA should be IB times L times BA, and in this chapter, we know that BA will be mu0/2 pi times IA. 2 pi d mu0 IA over 2 pi d is BA. So the force either attracting them or repelling them is something like this. mu0 L IA IB over 2 pi d. D is the distance between them, the wire separation. IA IB is the current in the wire. So if IA and IB are in the same direction, they attract each other. If they're in opposite direction, they repel each other. Find force on a current carrying due to the second current carrying wire. First find the field, okay. So this is what I mentioned just now. You determine the magnetic field generated by one wire acting on the other wire, and then you use the Lorentz force to find the direction of the force. Then you will know that whether the two wires are attracting each other or repelling each other. Similar to anti-parallel, you could show that two wires repel each other. So in short, you can say that parallel current attract each other and anti-parallel current repel each other. Parallel currents mean parallel wire with same direction, with the current in the same direction. Antipare means parallel wire with current in opposite direction. So it is pretty easy. Any questions? Okay, let's come to Ampere's law. Ampere's law is the next law in the Maxwell equation. So for Gauss law, you see that you saw that is something like a Gaussian integral, which is a double integral for a closed surface. And actually, you here you also see a similar but not really the same notation. Actually, this is a line integral. This is a line integral. For that one, it is a surface integral. Usually in math book, the notation would be more specific. More specific. Maybe I just usually for Gauss law, you something like this, something like this. You write it something like this. So actually, this is what we call the surface integral. In math book, more specifically, it will something written like this, because it is actually a double integral. So you have two integral signs to specify this is a double integral. But here we'll see that it is something like b dot ds. Actually, this is a line integral, which is something like suppose you have a B field, and then usually we'll also write here. For example, if S is a Gaussian surface, we'll write S here to specify that this double integral is calculate over this surface, and this is a line integral which is calculate over a contour. For example, this is called C, and maybe we calculate in this direction counterclockwise. So for every point on this contour, you have B, you will have something like ds, something like ds, and at this point, the B may be in this direction, B at this point. So you calculate the inner product between B and ds, and of course we separate this contour into in many infinite small segments, and then we add all of them together. Then this is the line integral. So we come back to here. So this for line integral, of course, you can calculate it through a line, but with this circle, it means it is a contour, which means it is close for a line, and we can call it Ampere loop. So this is Ampere law, we call it Ampere loop. For Gauss law, we call it Gaussian surface. Similar concept in here. So this is actually a closed loop, and we call it Ampere loop. So for Ampere's law, we can say that uh, so B is a magnetic field, and for a Ampere loop, this showing here is an orange line. The line integral over this contour will equals to mu0 times I enclosed. I enclosed means the current going through this contour, because this contour has a surface, and we only count the current going through this surface. So I1, we just remove all them. So here I1 is pointing outside the page, and I2 pointing inside the page. So for this one, we have B dot ds to be equals to mu0. Well, maybe you can write, okay, it defines the direction. It defines the direction counterclockwise d. So this will be something like I1 minus I2. According to the right-hand rule. So this is going counterclockwise. So when it is going out of the page, I1 is positive, I2 is into the page, so it is negative. So here we'll write mu0 I1 minus I2. If the Ampere loop is defined clockwise, then we will something like mu0 I2 minus I1. Similar to Gauss law, we only for Gauss law we only calculate the charge inside the surface. So for Ampere's law, we also calculate we only calculate the current going through this Ampere loop. So I3 is out of the loop, so the effect of this current to this line integral is 0. Of course, they will generate some well, maybe some. So actually, you know that. Maybe I just remove all of them. For example, you can see that I3 will generate a magnetic field, something like this, right-hand rule. So it's going counterclockwise, and actually something like this, which is even stronger because it is something like mu0 I over 2 pi r. So if when r is smaller, then this is even stronger. But okay, this for this part this is positive, and for this part it is negative, because B in this direction is in the opposite direction of ds. So this is negative, this is positive. So overall, for I3, overall these line integrals will be 0, as long as this is outside the loop, and I1 and I2 are inside the loop. So we only count I1 and I2, and the positive or negative depends on the direction, and follows the right-hand rule. Curl your right hand around the Ampere loop with the finger pointing in the direction of integration. A current through the loop in general direction of your outstretched thumb is assigned a plus sign, and the current generally in opposite direction is assigned a minus sign. This is what I've explained just now. And this is how to assign sign to a current using Ampere's law. Any questions? Okay, so actually, just now we can see that the magnetic field generated by an infinite long wire will be something like this. B equals mu I 2 pi r. Actually, using the Ampere's law, you can get it very easily because B dot ds will be something like, suppose you have a Ampere loop like this. This is the Ampere loop, and this is the current. This is the current. So we can write it B dot ds will be something like B times, this is R. So B times 2 pi R equals mu I. And you divide 2 pi R on both sides, then you get B equals mu 0 I over 2 pi R. Of course, it is not a proof. There's not a proof for this Ampere's law, but it will be very helpful when you really need to calculate the magnetic field. So using the Ampere's law, we can calculate even more complicated situation. The magnetic field of a long wire with current. So suppose we have a wire. The radius of this wire is small r. Small r. So we can know that the magnetic field outside the straight wire is something like this, which is nothing but to have a wire which is infinitely thin, similar to the Gauss law. Suppose you have a charge distribute at a point, then you can know the electric field is something like 1 over 4 pi epsilon 0 q1 over r squared, and it is equivalent to the charge is distributed on a metal ball which is distributed on the surface of it. And this is similar to that case when it is outside the straight wire. B will be something like mu 0 I 2 pi r. But when r oh sorry, this is not. Oh, this one should be capital R. R should refer to the center point to the Ampere loop. Ampere loop. So for this case, it should be something like R larger than capital R. And for this one, R should be less than capital R. And of course, R, when R is equal to capital R, these two are the same. And using the Ampere's law, we can show the magnetic field is something like this. Okay, we have the Ampere's law. So on the left-hand side, it is nothing but B times 2 pi R. And the right side will be something like mu0 I r square over r square. Because the current in this wire is uniform, which means that we should have I enclosed over pi r square, which is the cross-section area, equals the whole current over pi r square. So this is the J. The J should be constant for both cases. And on the right side, we concern is the I enclosed, so we multiply pi small r square on both sides, and pi can be cancelled. So what we have is I times r square over capital R square. So we divide 2 pi r on both sides so that we can have 2 pi r square mu0 I times r. So this is the magnetic field inside a strict wire. Any question?